So Valgrind is a suite of tools for debugging, profiling, and the usage analysis. And there are several tools here. Memcheck is probably the most well-known tool that is used for detecting memory errors or memory leaks. And another one is a Valgrind. This is to measure the number of instructions as a proxy for runtime, for the time when you do a profiling your code. It does mimic the cache usage here, but the manual these days says that not to rely on that. So probably the main usage should be the profiling your code in terms of executed instructions. Valgrind is similar to Valgrind, but it is more sophisticated. It records the core history among the functions so that it can give a more better perspective regarding which function is using how much, for instance. So again, this is using the number of instructions as a proxy for runtime. Massive is a heap profiler. It's a simple, and it shows the heap usage over the run of your code. And another one is a DHAT. This is a dynamic heap analysis tool. This is largely about analyzing how you use the dynamic heap memory during your run. So this is a very interesting tool, actually. I find that this can be useful. So using this information, saying that how many times a certain memory block was used during a run, so you can rely on this information and then you can optimize your code, for instance. Valgrind and VLD, P-threads error detectors, and some more. And as Justin said, that Valgrind works for C, C++, and Fortran. And what these tools do is they add their own instrumentation at runtime, not compile time. So because of this instrumentation, the code runs a lot slower. So this is just used for debugging or profiling. So initially, we plan to cover many Valgrind tools, but it turns out that we don't have enough time. So this time, we want to focus on the Memcheck and the Valgrind, Valgrind, Massive, DHAT, Valgrind, and the DLD can be maybe for future training. So how do you use a Valgrind? This is you have to build your code using the -G flag to include the debug information. For error detection tool like a Memcheck, you better use the do optimization at all, so that you can easily track the function call and see that where that the function call is made. For the profiling tools, you should use the higher optimization level. So, but for the Memcheck, you have to use the no optimization. And this is a Valgrind command. Valgrind, and you specify the tool that you are going to use. If it is a Memcheck, you can omit that because Memcheck is the default tool, and you add the Valgrind options in the program and the program options. So Memcheck, as I said, is mainly to detect the memory errors. So these are the types of errors that you can detect: out of bounds access or heap array, accessing uninitialized memory, incorrect freeing of heap memory, like double freeing heap memory, or you're using the wrong command for freeing memory, or you can detect whether that the source and destination pointers are overlapping in the memcopy command, or you can detect the misaligned memory allocation. Also, you can detect the memory leaks. So what the Memcheck does is actually it uses 2 extra blocks for bookkeeping the state of memory block. This is called the VBIT, the memory block is called a VBit. That is to check whether the values are valid, so whether the values are defined or not. And the second one is A-bit. This is to check whether the address is valid. Are you trying to free the memory block that was freed before, for instance? So each byte in memory has 8 V bits. That is 1 byte, so 1-to-1 correspondence here, and a single A bit. So again, this is how to invoke Valgrind here. So Valgrind and memcheck invocation. You don't have to specify two names because memcheck is the default tool, and you can add other Valgrind options. And as you see that you can use some common memcheck options as shown here. --leak check. If it is set to full or yes, you can show that the detail about the memory block that was reported as leaked. So like callback traces. And if we use a --track --origins, yes, then you can actually show that where that the memory block was allocated. Again, it shows the callback trace here. And another popular option is a --, suppression, because memchecks report many errors that you don't have to worry about, like from the system library, etc. So you may want to suppress them so that the output can focus on the output from your own code only to debug your code here. So as an example, the first example is to find the uninitialized value using the memcheck. Here I'm showing the test code here from the manual. So as you can see, we define the integer variable x, but the value is not initialized. The value is not given. But yet in line 7, that the variable is checked against the certain value in the if block. So this is, if you compile this code using this -g and the -00, and if you run it with the Valgrind, it will show that the error message regarding that uninitialized value. Actually, Valgrind checks the uninitialized values when the program uses conditional code here, conditional statement in a certain situation, not all the situations here. So they use this error message like conditional jump, right? And another simple example is to detect the illegal freeze here. You see that the example code on the left, the bottom left here. So we use a pointer P to allocate the memory block of 177 bytes. And we have a for loop here. So the code is trying to free that memory block allocate using the P 2 times actually here. So this is a too simple example actually, but if you run with a Valgrind, as you see that there's an invalid free in the second time, right? Because you are trying to free a memory block that was freed already. So using this, you can, and then also it lists the code where the memory address was allocated, etc. So the one big items using that you can do with the memcheck is to detect the memory leak. So why the memory leak is important? Memory leak is when the program dynamically allocates a memory block, but it doesn't free it after its use, and then the block cannot be reused, and then and it reduces the available memory that you can use by the program. If a function with a memory leak is called repeatedly, the available memory will become less and less. reducing capability of that. So like if a given number of compute nodes, you expect to run certain fine resolution calculation. But if there is a memory leak by a large amount, then you cannot run that fine resolution calculation using that many nodes. You may need additional nodes, for instance. So you are wasting your resources here. So it is important to detect these memory leaks and fix them. So the mem check uses these terms, the start pointer and interior pointer, to distinguish different types of memory leaks here. A start pointer is what we are usually familiar with. Start pointer is pointing to the start of allocated block, as shown on the bottom left of the diagram. And the interior pointer is pointing to the middle of the block, as shown in the bottom right. So the common case that we have of this interior pointer is that even though we start as a start pointer, we can increment the pointer, right? So that you can go over element by element like that. And when program exits, then pointer is pointing the interior somewhere in the middle. So that can be a problem. Or sometimes the compilers allocate some metadata about the memory block that is being allocated before the actual data block. So I'm not really familiar with the C++, but this is what the compilers do. Like they put their size values in the metadata section here. So these are the 4 memory leak types reported by memcheck. So the first one is still reachable. That means that you can always reach the memory block starting from the pointers available at the program exit, because it reports whether the memory blocks are leaked or not after the program exit, right? So in this case, block AAA can be directly reached from the pointer, such a pointer, but the memory block BBB can be indirectly reachable. So they are still reachable when the program exits. Yeah, but still, this is a bug. You should, even though they are reachable, you should actually free them, but you didn't. For instance, so you have this still kind of the problem you have to fix. And the second type is definitely lost. So there is a memory block, but there is no pointer pointing to the memory block at the end of the program. So there's no way to free that memory block here. So this is a probably more serious problem than the previous one. The indirectly lost type is a memory block can be reached by by a pointer in another memory block, but that memory block cannot be reached from the pointers, the user pointers. So in this case, indirectly lost. And the last kind is possibly lost. These are the memory blocks pointed by all interior pointers that I mentioned before, directly or indirectly. And actually, you can provide some more heuristics, like the C++ related cases, context, to drill down whether the memory block is still reachable or definitely lost, something like that. But the memcheck doesn't do that by itself, so that they are classified as possibly lost. You can take a look at this block. It has many simple example codes to show that what types can be classified as possibly lost. what types can be classified as still reachable, etc. It's a pretty interesting block. And this is a simple example here. This code, the pointer x allocates 10 integers here, so 40 bytes. It allocates the memory block of 40 bytes here. And then in line 6, it allocates 11th element here. So this is a heap overrun, out of bound the memory access here. So there are 2 errors here. And then it exits the function f without freeing the memory block that was allocated with the pointer x. So we have 2 types of issue. Here we build it like this. And when you run Valgrind using the --leak check was full, as you can see that the first group shows that the error about invalid write of 4 bytes beyond the allocated memory block here. It shows that where that the error was made here, line 6, and that memory was allocated in line 5. And this heap summary again summarizes how that the memory block was allocated. And at the bottom here, we have a leak summary. It shows that definitely lost section. We have 40 bytes in one block, definitely lost here. So for the next few issues, I'm going to use the MPI code. So we have a very simple-minded MPI version code here for the memory leak here. So we put a MPI, we wrap with the MPI pretty much here, right? And then the rest is similar. Other than that, we have a larger memory block size. So then how do you run the MPI code with Valgrind? The way to do it is you make the Valgrind output a separate, use a separate file for different MPI rank using you specify that where that a certain MPI task output should go. So for that we use a %p specifier or %q. %q is to use some environment variable. So slum_proc ID is for MPI rank. So we can try this command srun n8 Valgrind leak check yes log file. This is log file name. We use a slum job ID and the slum rank, and we run this MPI code. Then we have 8 output files here. And one minor note is that the mcheck can wrap MPI functions so they can check the validity of MPI function arguments. But it looks like it is not working with the Cray MPI. If you want, you can test it with the 3.23 version of Valgrind. So, I'm sorry, wrong direction. So another important topic is the suppressing error, because Valgrind memcheck reports so many errors here. So memcheck occasionally produces false positives or errors in the system library that you cannot change or you don't care. So you can focus on your own code here. And to get the first thing is that you have to create a suppression file. So you get all the suppression expressions by using this flag, and then you put the suppression, the correct suppression format for all the errors that the memcheck detects. And then you basically go over this file. It can be a tedious work, and then you can only keep the errors that you want to suppress, not the errors, not about the errors from your user code, for instance, right? And then use that suppression file using this flag, and you run the memcheck. Valgrind by default uses some suppression file, so can be in this form. The file name is a default.sub. So this is how to get the how to suppress file, how to generate how to create a suppression file and then use it. So you can use probably N1, Valgrind, leak check full, and gen suppression all, and the log file you specify the output file name, errors, and run it, and you get output errors. And then what it does is that we are trying to grab the file for the lines that don't -v inverse graph don't start with a dash line, a dash equal sign, double equal signs, and they save it as MySub, and you edit the suppression file. This is how the suppression file looks like. The first line, the one suppression is basically contained in the pair of this curly brackets here. And the first line is the name of the suppression. Second is to specify what the suppression is for. This is for using for the memcheck tool. And the con is that it is trying to use undefined value in a conditional statement. So this is a predefined keywords, basically cont. And then after that is to provide a calling context. So what it means that this error happens in function add underscore entry, which was called in -n underscore get, etc., and all the way down to the main. Here, fun is for function. So this is function name, it means. And the 3 dots is a special meta character, is a special wildcard that's for frame level wildcard. So it can be 0 or more frames here. So they can be just no function call between this line and the main, or there can be many. So we can use this simple form, and then we use the data suppression file. And then when you use it, we get the report saying that 7 errors was suppressed. Okay, this is how to create a suppression file and then use it. So Valgrind4hpc is a HPC tool that aggregates the multiple Valgrind messages over MPI process, so that we only want to have a single output file. But if they have a duplicate error message, then we can group them so that we indicate that where that this message is for what group of MPI ranks, for instance. So it's simpler to handle for us. And also another big benefit is that it uses the suppression file. There is suppressions. The suppression file that suppresses the errors, the known errors in the HPC software. So if you go to this directory, they provide for the suppression file. So it uses these suppression files all the time. You can actually use these suppression files without using Valgrind4hpc, but you own Valgrind run if you want. And this tool works currently only for memcheck, Valgrind, and the DLD, not other Valgrind tools. So to use it, you load the Valgrind4hpc module, and then you run like this in a batch session. Right? This is, you should have a SL or something, or SBatch, whatever. And the Valgrind4hpc -N8, I'm launching 8 MPI ranks. And you pass the Valgrind arguments using Valgrind args flag for short -v, and run this one here. This is out. So we get basically the same output here as the serial one, but it starts with the rank group. So it says that rank 0 to 7 has the same output like that. You invalidate that right, and the rank 0 to 7, 40 byte will allocate, something like that. and that is heap summary for the rank 0 to 7. And it says that it suppresses 601 errors. So this is really useful tool. I mean, the tool is a really embarrassing in parallel code. So each rank does the exactly same thing, and that this is what is expected actually. So another thing that we find interesting, might be interesting for shortcode is a heap. We can profile heap usage using what they call the execution trees. So execution trees is made of for the set of stack traces for certain resource consumption or certain event accounts. For instance, if a code allocates a memory block, then there is an execution tree, the calling sequence for that event here, right? So we use these are used for graphical or textual representation of resource usage here. For in this case, memcheck with heap usage here. So and then we get the output in the Valgrind or massive format. They are the two other Valgrind the tools, and then use their tool to process this data into a human readable form here. So to do that, I'm not really sure, but I found that some error when I didn't remove the darshan module. So you can probably do the same thing and run Valgrind using this special flag x3-memory equals full. And then you specify the output file name. .kcz means that we are the output in the Valgrind format, and .ms is for massive format. And then you post-process this output using this sorting. We want the output sorted by Kirby, whatever that means, which I will explain in the next slide. So, and then you print out the ASCII text output, or you can use the Valgrind4hpc like this. So this is output. It shows that the Kirby is the current number of bytes allocated. So whatever that ends with K means the number of blocks, okay, not the bytes. So we have 195 kilobytes allocated over the for the total allocated amount is 195 kilobytes over 602 memory blocks, etc. This total number of blocks, total number of memory allocation, total free bytes, and total freed number of, the freed blocks here. So, and also you can show that, function-wise that where, how much memory is being used, like this. And then you can annotate the source code like this. So it says that this line allocates this much memory here, and the MPI init allocates this much memory, and MPI finalize free certain amount like that. So it can be useful for short code. I'm not sure how it can be useful for long code. Cannot actually display all the source code like that, but you see that this is available. You can do the similar thing with the memory leaks. So you use a different flag. This the memory leak equals CS. You specify name, and you basically it shows the reachable bytes, possibly lost bytes, indirectly lost bytes, etc. So you post-process and to get the output. It's a pretty long output. So that's all about the lecture here. So for the hands-on session, there are multiple Valgrind versions on Parameter. So system provider Valgrind has a version 3.18.1. And also we have a Valgrind modules. The latest one is 3.23.0. And Valgrind for HPC comes with our own Valgrind as well. This one's 3.20.0. You can use any of these for today's exercise, even though that we prepared the training material using the system provided one. And we may retire Valgrind modules in the future. So for hands-on material, you git clone this repo and the CD to that the Valgrind memcheck directory, and follow the instruction in the README file here. So, and if you are interested in, then you can try the Fortran code in the Fortran_memory directory as well. There be any questions? So in that case, let's do the hands-on exercise here. So if you have a question, just let us know. Yeah, go ahead. Yeah, you can ask questions. So what is the Rust code? So actually, you can run the Valgrind on anything. Actually, you don't have to compile. You can actually run the Valgrind on the compiled code already. So you can just try the
Rust is a different programming language, Wusan.
Yeah, I see.
I don't think that it works with Rust.
No, it's probably, you can try, I can, the manual actually, when you read the manual, actually it runs on the ls command. So, as a first example.
Let's see here.
So just try. But you may not get all the debug information. I'm not sure. These are the README file for memtrack. So you follow basically. So if you are dealing with the serial code, you can run on the login node. You don't have to run. You don't have to get the SL log or SBatch here. But for MPI code, you have to allocate node and then run it using SRL. Oh, how about the Cray and pitch incompatibility? I mean, that is about the wrapper, MPI wrappers here, right? So the manual actually says that it is probably targeted for OpenMPI. It mentions OpenMPI with the GNU and the Intel compilers. So I went ahead and then built the 3.23.0 version for the Cray and pitch, and then I couldn't get the output, the expected output. I was using the buggy MPI code, hoping that it would catch the error with my arguments, but it didn't. So I don't think that it'll be fixed, but just to let you know. So it'll be really nice that if somebody MPI is send the command, for instance, you only send the unallocated memory pointer. For instance, you can detect. But I just tested very few things, but yeah, I don't think that it'll be fixed. Yeah, about the memory leak errors. So yeah, there are many memory leak errors associated with your system libraries, MPI libraries, for instance. But we don't care and we cannot fix, right? So we only want to fix the memory leaks in our own code. So that's why we are using suppression here. And yes, we are, a sample example has some the memory leak example. Yeah. So memory leak can happen in the system libraries and the user codes. Yeah. Yeah. About the Valgrind, IDE, I do not know. I haven't read from the manual anything about that. Yeah, so no.
You know what TV show made me really wary of having kids? You guys ever see that show, The Nightly News?
Can you repeat that?
It was someone who wasn't muted. I muted them.
Okay, all right. Do you have any questions regarding the hands-on?
When I'm trying to run the S run, it says unable to create step for job, more processes requested than permitted.
So you have to SL of the you have to run the SL command before so that you can get into the compute node. Then you can run that.
I'm on a compute node.
Yeah. Basically, MPI code doesn't run on local node.
Yeah, I understand. I am on a login. I am on a compute node.
Okay. So what else do you ask on command?
So the SL command I ran is the one from the Q&A, and the srunner command I'm running the one that's on the README.
Okay. So here, this is to use are you using the CPU code, right?
The CPU, yes.
Yeah. So maybe you can, if you want to, you're using 8, you said? Then you can use, for instance, -n, -c 16. And I'm sorry, can I do that? Let's run.
Okay, I'll try that.
Yeah, for SL. Or you can actually request the entire node.
Yes, now it's working. I think the issue was because the SRAN has -N8 in the read.
Right.
So we should also salloc minus n8.
Oh, actually, this. Yeah, actually, you should have. Sorry, I was wrong. You should have done this. Yeah. No, I'm sorry. I'm doing it wrong.